All right, we're working now still in the second half of Chapter 2, and we're looking at the principles of eclipses as they relate to solar and lunar eclipses. And so the first thing that I wanted to do is to define what an eclipse is in general, and then we'll relate it more generally to, or more specifically I should say, to a solar and a lunar eclipse. So an eclipse in general happens when an object blocks the light from a star. And so that could happen then when, let's say, the planet Venus moves across the solar disk. Okay, and so this kind of a eclipse is hardly noticeable. I mean, you could see it with a really good telescope, but Venus is not blocking much of the light. Another way that something like this could happen is that you could have a moon of Jupiter blocking the light from a star. Okay, so here's your star, and then this moon of Jupiter gets in the way of it and blocks the light. So that would also be an eclipse of object getting in the way of light that's coming from a star to our eyes. And if we look up at the upper projector, we see that a solar eclipse is a little more specific than that. A total solar eclipse occurs when the moon is between the Earth and the sun and blocks the light from the sun over a small part of the Earth's surface. Okay? And so that's a complete blockage of light, but just over a small part of the Earth's surface. Whereas we can also define a partial solar eclipse as occurring when the moon isn't quite directly in the way of the light that's coming from the sun. And so we can see the configurations for both a solar and a lunar eclipse here. Here we see the moon is right between the Earth and the sun. And so that creates a complete blockage over a small part of the Earth's surface, but then a lot of you have probably seen partial eclipses much more often than you have total eclipses, if you've seen any total eclipses. Whereas a partial eclipse means that the moon is partially blocking the light from the sun, but it is not completely blocking the sun's light. So it just takes a little bite out of the sun, essentially. And then if it turns out that the moon is closer to the Earth than normal, or I'm sorry, farther away than normal, then you can get an annular eclipse. Because if the moon is farther away, then it looks smaller relative to the Earth-Sun system. And so we'll look at all of those examples as we go. And here's an example of a total eclipse where the moon has gotten directly in the way of the light that's coming from the sun to the Earth. And here, this upper picture is actually a satellite picture in which we can see that region of total blockage of light. Okay, so if and we can't draw this fully to scale, unfortunately, but we can draw it to the extent that we can see what's going on in the problem. So here, if the centers of the Earth, Moon, and the Sun are along a straight line, then we can get a blockage of the light over a small part of the Earth's surface. And this region of total eclipse is called the umbra. Okay. And then surrounding that is a region of partial eclipse called the penumbra. And since the penumbra takes up such a larger amount of space, it is clear that this is the reason why we've probably seen some partial eclipses, but maybe we haven't been quite so lucky as to have seen a total eclipse of the sun by the moon. Okay, so, but we might wonder, well, how is this little dinky moon able to pull this off? How can it block all of the light that's coming from the sun? And this, by the way, is the kind of thing that you would see if you're looking at a solar eclipse, is you'd see the solar disk completely blocked out. But it's spectacular because you would see the solar corona still. And actually, astronomers do study the properties of the solar corona during solar eclipses. And some of them actually run along with the Earth at the speed that the Earth rotates in order to maintain that position within the shadow longer so that they can study the corona for longer periods of time. Here's another picture, and this shows basically the same thing but with a different looking corona. And so the corona has different levels of activity, and it fluctuates over time depending on what's going on inside of the sun. But we might wonder, how is the moon able to block the sun's light? So a solar eclipse is possible because, first, the moon is 400 times closer to the Earth than the sun. And two, and this is an amazing coincidence, the moon is also 400 times smaller in diameter than the sun. And so we have the apparent or angular size of the moon and the sun are about the same. That's the result. It's smaller, but it's closer. It's 1/2 of 1 degree for both the moon and the sun. Okay, and so that may seem like a little small, because if you sweep across the whole half plane, looking from horizon to horizon, you're looking through 180 degrees. And so if the sun is only 1/2 a degree, that means that you could take 360 suns, put them edge on edge, without them overlapping, and it would cover the sky. So it just seems like the sun's bigger than that. But one of the reasons for that is that it's too bright for us to even dare look at it. So it kind of captures a lot of effective space around it because you're afraid to look in that direction. But if you held out a quarter at arm's length and had it just fill up the full moon, then you took that same quarter at arm's length, it would just fill up the sun too. And so that's the way that you can prove it. Even though it looks like sometimes the moon is bigger when it's near the horizon, that's just an illusion. And it's based on the fact that the mind judges size by the relationship of that object to other background objects, or in this case foreground objects when you're talking about the horizon. Okay, so the moon then is smaller, but it's also closer. And so the angular size, for example, of this pin, if I bring it in really close and I measure the angle, it's like 90 degrees. If I bring it out to here, I measure the angle, it's only maybe 30 degrees. Okay, and so just the closeness of an object affects its apparent size, and that's something I think you already know. If you think about it for a second, that has to be true. Okay, so why is this an amazing coincidence? Well, because the moon has been moving farther and farther apart from the Earth for billions of years. And so we've actually put mirrors on the moon and measured how much farther away it gets each year by bouncing laser beams off of that mirror. And so a lot of people have been arguing, well, we never made it to the moon, that was all just faked. No, that's interesting then, because how do we get those mirrors onto the moon that we use to reflect the light back? We've been able to show that the moon moves away from the Earth something like 3 inches a year farther away. And so that doesn't sound like much. But if you work that out over geologic time, billions of years, that means that maybe 4 billion years ago, the moon looked like a dinner plate held out at arm's length, rather than just a quarter held out at arm's length. And so it was huge. It was generating gigantic tides. Every wave was a tsunami. You'd be 1,000-foot waves. You'd be killed if you were a surfer back in those days. But there were no surfers in those days. But as time went on, the moon is moving farther and farther out. We'll talk more about why that's true when we get to tides later on. But for the moment, we can just say that that is the case, and as the moon continues to move farther out, eventually the Earth may actually lose its grip on the moon. Or the moon will get so far out that it's no longer able to stabilize the Earth's rotational axis. And so many things can happen in the future, and also total eclipses will be a thing of the past in the future as well. Okay, so with those ideas in mind, let's try to answer the question as to why we don't get a total eclipse every month. And the answer to that question, first, let's draw this. If the moon were in the ecliptic plane, then we would. So this would be the sun, this would be the Earth, this would be the moon. So if the moon happened to be in the ecliptic plane, we could get a total eclipse every month as the moon moves around the Earth, because it would always be blocking the light from the sun when it got to this near point. But that's not the case. The moon moves around the Earth in an orbit that's about a 7-degree angle to the plane of the ecliptic. And so what this means then is, the sun way out here, try to keep it a better perspective, is that when the moon is at its closest distance to the sun, between the Earth and the sun, normally the shadow of the moon misses the Earth, and the shadow of the Earth misses the moon, so that we don't get a lunar eclipse when we're over here on this side. Okay, but occasionally you can get a total blockage, and I think this picture might explain that a little better than I can do with my pictures. And so we can see here then that the kind of configuration I was talking about, where the moon is orbiting at an angle that's about 6 or 7 degrees to the ecliptic plane, is that the shadows miss each other. And so that way you just get your normal full and new moon, and you don't have to worry about eclipses every month. But because that angle of the moon's orbit maintains that same angle as the Earth goes around the sun, see that there are points in the year when it's possible for the moon to cross the plane of the ecliptic, going from below to above, at just the point where it's exactly between the Earth and the sun. Okay? And so it always has to do that. Over here in this position, the moon crosses the plane of the ecliptic here and there. Okay? So that's not in the way of the Earth, right? But over here it is. So when it crosses and it goes to above the plane of the ecliptic here, and it just happens to be along that line that's between the Earth and the sun, it's unusual, but it can create an eclipse effect. And then similarly, when it's on the other side, then the shadow of the Earth can block the light to the moon, and that's what we will call later on a lunar eclipse. Okay, but then we come back around to this point. Notice here again that the angle of the lunar plane is similar to how it was over here relative to our position with respect to the sun. And so then you have your normal lunar phases, and it's unfavorable for eclipses. But when it comes back over here again, it's still crossing the plane of the ecliptic at those 2 points when it's along that line between the Earth and the sun. And so then the here and there then are favorable for eclipses. But they don't happen twice a year because a lot of other things have to line up in just the right way for this to happen too. It's a little trickier than this. The moon's long axis of the ellipse actually changes its direction as time goes on too. And so this makes it much more difficult to calculate. But it's fairly rare for this to happen. Okay. So the answer then is that the moon orbit is inclined with respect to the ecliptic plane. And so because of that, the shadows from the moon and the Earth miss each other. Mostly. But occasionally, as we mentioned, it's possible for the shadows to be lined up with that straight line between the Earth, Moon, and the Sun. Okay, so what's the variations on this? Well, you can also get an annular eclipse. So during an annular eclipse, the moon is at its most distant point. From the Earth. When the moon is between the Earth and the Sun. And so because of this, because the moon is farther away than normal, the light could only be seen as a total eclipse if you flew up to this point above the surface of the Earth. So in other words, the moon looks smaller from the standpoint of the Earth. And blocks less of the sun. And so an annular eclipse tends to look more like this. Here's the sun, and then here's the moon. It's doing its best. But it's not good enough. It can't block all of the light from the sun. And so a little bit of the sun's light leaks out from around the edges. Okay, so you have the annulus is like a donut. Okay, and so basically here, this is all dark. And then you've got this little rim of light. So here's what it would look like. Here's a picture of an annular eclipse. And they are quite spectacular, but you need to have some kind of eye protection to keep from burning your retina in this kind of a situation. Here's a picture where the moon is progressively getting more and more in front of the sun until finally it's aligned perfectly, but it's annular. So you still need to wear really good protective goggles to protect yourself from the searing bright light that is coming out from around the moon. Okay, and then here are a few pictures of eclipse paths from previous eclipses. The yellow is, or the red I should say, is total, okay, and the annular are the blue ones. And so we are getting a few blue ones here. This was from August 3rd, 2005. Here we have a total eclipse from December 4th, 2002 and June 21st, 2001, and they cross over at this point. So these two lucky, or this lucky group of people in Africa, able to see two eclipses within 6 months of each other. This was June 2001, this was December 2002. So why are the eclipses in a path like this? Well, when we get a total alignment of the moon just right in the way of the light that's coming from the sun, you might say have a total eclipse at this point. But now the Earth rotates out from under that point, and so that creates your eclipse path. And so there was an eclipse back in 1991, and it went through the big island of Hawaii, and then went through Baja, went close to Mexico City, and the people that went to see it in Hawaii were out of luck because the eclipse itself can change the weather. And it brought in a bunch of fog and clouds, and even on the top of Mauna Kea, they were barely able to see anything without a lot of good filters. But the people that went to the Baja and the mainland of Mexico got a lot of really good eclipse viewing in. And so you do have to be careful with eclipses that you don't go to a location where it's susceptible to fog or things like that when the eclipse starts to roll in. Another eclipse in Paris, they were just all set for this one. They're ready to party. They had swimming pools filled with wine, if you can believe that. But the fog tended to come in as the eclipse started to form. But these lucky people out here that went to Turkey got some really good views of the eclipse because this is more dry weather here and there's less tendency to have climate conditions be unfavorable for an eclipse. Now for us, the next main eclipse that'll happen for us is in 2024, and that'll happen in the eastern part of the United States. I missed the one that was up in Oregon a couple of years ago. And so this time I'm going to fly to a city that's right on the eclipse path and just get a hotel there so I don't have to drive anywhere. And I'm going to view it from there. But that's in the summer of 2024.